All right, let's start with the obvious question. In the context of Iceberg, what is partitioning? So imagine a table with billions of rows, very large table. And this is not an uncommon thing in a data lake. And let's say you need all the sales from last Tuesday. Without partitioning, the query engine has to scan every single file to find them. That's not great. That's going to be a lot of scanning. It's going to be very costly, take a long time. With partitioning, the data is organized such that the engine can skip files that don't matter. On the read path, that's called pruning. That's a very important part of how the query engine is going to optimize its work. So think of it as the difference between a clean filing cabinet and a giant pile of papers. Back in the day, partitioning meant creating physical directories for each slice of data, like month equals 01, month equals 02, and so on. It worked, but it was really rigid. You had to build that in to the physical structure of the data, which means if you want to change your partitioning scheme, good luck with that. You actually have to move things around into new directories. Probably not move, probably actually copy so that the old thing is online while the new thing is coming online. That's a lot. Iceberg takes a different approach, which it calls hidden partitioning. Partition information lives in the metadata layer, specifically in the manifest files, while data files can be physically anywhere. So no physical directories, no rigid structure, no partitioning scheme that you're committed to when you load the data. That gives you some pretty powerful benefits. Let's once again create a sales table. We're going to partition it by sale date and region. And you can see that there with the partitioned by keyword. Notice something? We're not using sale date directly. We're calling that months function, months on sale date. That's called a partition transform. It's built into Iceberg. It gives you efficient month level pruning now without having to create a partition for every single date, without having to derive a column that's just got month or any of those shenanigans. You don't need an extra column. Iceberg handles that transform automatically. Here's a manifest file for this table, a little bit simplified for our purposes. There are 3 entries in the manifest file. Each is pointing to a different data file. The first one points to file 001.parquet sitting in the warehouse sales data path in our S3 bucket. Now let's look at the partition values. Instead of storing the raw sale date, Iceberg stores the transformed value, months sale date, calling that months function, which equals 627. That's March 2025, plus the region, which is US, because both those fields were in the partition declaration. When you query the sales table for a specific date, Iceberg knows exactly which partition to check. The date that you want is in the query, that's in your predicates, and the metadata says which dates are going to be, or more to the point, not going to be in each data file. So for this query, whose predicates specify March 2025, US region, the engine is going to know to scan exactly one file. And that's going to be that top data file, file 0001.parquet. There are many built-in partition transformations. For time, you saw months. There's also years, days, hours, all really efficient for time-based partitioning. If you have data that you want spread evenly across, say, millions of users or some other very high cardinality kind of column, you can use bucket. If you have high cardinality product codes, truncate will group them into manageable chunks. You don't reference any of this in your queries. You're just writing a where clause at the time that you're reading. Iceberg handles the transforms automatically and handles the pruning automatically in the read path. Now, what if you have to change a partition? That's partition evolution. And very, very likely you're going to be doing that on a table that's full of data and partitions that are full of data. With older pre-Iceberg table formats, that kind of change was a headache. You had to pick a directory structure like year, month, day, or something like that seemed like good partitioning at the time. When you did that, you were stuck with it until you rebuilt the whole table. Again, physically copying that data around. With Iceberg, it's simple. You can evolve your partitioning anytime your needs evolve, potentially without rewrites and hopefully without pain. For example, your sales table is growing like crazy. Good news, good job. You've done really well. Those monthly partitions are starting to get a little unwieldy, and you might want to switch to daily. With Iceberg, it's a simple partition spec update. You drop both partition fields, as you see here, and then add them back in the same order. And the second time around, it's the same sale date column, but of course, a different transform. You got days instead of months. And the change here, this is key, only applies to new data. Okay, the old monthly partitions, those are data files, and those were partitioned per month. Those are going to stay the way they are unless you do something to rewrite them, which you'd probably rather not do. So scanning on those old monthly partitions, if there's a query with a day predicate, might not be as efficient as it could be, right? You're still going to have to scan that whole month file. But now for new data going forward with the new partition scheme, which is days, we'll have day partitions. We'll have more efficient pruning, more efficient scanning on the new data. Again, at query time, you don't know any of this. It could affect query performance. You're just writing a where clause. At that point, you know nothing about partitioning. So you can pretend you know nothing about partitioning. This just applies to the definition of the table itself. Now, here's what it looks like visually. Say we've got a query asking for sales between April 14th and May 9th. And we did that repartitioning at the beginning of May. So April is partitioned for by month, and May 1st going forward is partitioned by day. So on the left-hand side, the old monthly partitions, we do have to scan the whole April partition because we want to get to the last 2 weeks. We got to get that whole partition because it's all we got. Over on the right, with the daily partitions, we can surgically just get those first 9 partitions and ignore 10 and after. The blue blocks show us which partitions are pruned and not scanned. The green blocks show us which ones are scanned. And the engine is, of course, scanning all these different partitions. It will stitch together the results and give you one coherent result set on output. You're probably wondering, okay, this is cool, but how do I decide how to partition my data? Well, it's a good question, and the honest answer, once again, is it depends on your query patterns. Partitioning is fundamentally a performance optimization, and so you have to know what your queries look like and what kind of performance SLAs you want for various kinds of predicates in your reads. Time-based partitioning is usually the safest bet if your data has timestamps. Most analytics queries are going to filter by time. If you've ever used a dashboard or done any kind of looking back at business data, you're going to know there's usually a date in there. So that gives you solid pruning and a good place to start. If you have high cardinality columns, there are 2 transforms that can come to the rescue. Bucket hashes data for even distribution. A bucket is the first one, and what that does is it uses hashes to distribute that high cardinality evenly into buckets. If you're, say, always joining on customer ID and you have a very large number of customers and customer ID is always a predicate, we'll bucket it, and now related rows, that is rows with the same customer ID, are going to land in the same file. And so that's going to probably lead to better pruning and less scanning. Truncate groups similar values together based on, say, a string actual value of a column. If you have a product code that starts with some common string and then has numbers that start to differentiate, you could truncate that to, say, the first 7 characters or something like that. And then those similar codes are going to partition together and end up being in the same data file. Both of those keep your partition counts manageable while enabling the most efficient filtering and pruning possible. You can partition on more than one column at a time. That can be very powerful, but it's a sharp knife. If you go overboard, you might end up with a lot of small partitions, and this is just another way to cause the small file problem to rear its ugly head. You don't want that. So you want to be careful with partitioning by too many columns. Again, you just potentially could end up with small files, and that's not a win for anybody. In terms of file size, now is probably a good time to say that you want to aim for partitions that are between 100 megabyte and 1 gigabyte, inside that order of magnitude. Too small, too much below 100 megabyte, you're going to have too much overhead. Too big, pruning doesn't work, lots of I/O getting those things back and forth. So that's a good sweet spot. Your mileage can always vary. This is a thing that an advanced user might want to really tune. And you always hear cases of people going really big and really small and getting great results. But starting out, if you want a rule of thumb, between 100 megabytes, 1 gigabyte, you'll win. So that is partitioning in Iceberg. You're not locked into a single scheme forever, like with the old formats. You can evolve your partition strategy as your data grows, and that evolution applies to that new data that's ingested over time. Keep old layouts where they are and query everything seamlessly. It's pretty flexible, pretty efficient, leads to some really good performance, and it makes life a whole lot easier as your tables scale.